Okay, so let's continue on with chapter 11. Chapter 11 is going to talk about shapes of molecules. And we're going to go over two theories, valence bond, which is the VSEPR, and molecular orbital, which is has more to do with physical chemistry and quantum mechanics stuff. So why is it important to learn about shapes? Well, when molecules are a certain shape, they can fit onto, whatever receptor shapes there is, and then we can taste things because of that, or maybe proteins will function properly because of it. There's so many things that has to do that's important with shape. So we want to go ahead and learn how we can distinguish shapes. So before this chapter, before we were learning how to draw the Lewis dot structure, the distribution of electrons, but we never talked anything about the shapes of these molecules that we're drawing. So before we want to go forward, we want to talk about what the VSEPR stands for, okay? So VSEPR stands for valence shell electron, so the VS part. So the valence electrons of any atom or a molecule here, and the electron pair, because it comes in pairs, right? And repulsion. So it's basically electrons are taking out space, they're clouds, and they push away from each other because they're negatively charged, okay? And that's the idea here, that we have different kinds of electron groups that we categorize. So lone pairs are one type of electron group. Radical electrons are another type of electron group. Single bonds is an electron group. Double bonds is one electron group. Triple bond is also another electron group. So basically, any type of bond is a group. Any type of lone pair is a group. Any type of single radical electron is also a group. Okay, so because they repel each other, they need space. When they need space, we have to pretend like it's kind of like you have friends that you're friends with, but they don't like each other. So when you all go to a party, you have to find a way to hang out with them, but make sure they're still far away from each other. Okay, so the furthest they can be away from each other, but still connected to you. That's the idea there. Okay, so remember, any type of bond is considered one group, and a lone pair is a group as well. Okay, so let us look at an example here. So if you wanted to count electron groups, what we're focusing on is basically we have to pick the central atom of the molecule and decide this guy is you and these are your two friends, or how many friends you have to consider. So in this case, we have to count friends as electron groups. So how many electron groups do we see here? I see one group around nitrogen, two groups around nitrogen, three groups around nitrogen. So basically nitrogen has three electron groups around it that it has to spread apart the furthest possible away from each other, but still connected to nitrogen. And that's the idea of VSEPR, okay? So we have to basically connect them together and then, but spread them out as far away as possible from each other. So who takes up the most space? The most space will be taken up by a lone pair. Okay, lone pair can push away the furthest. It's kind of like the person that comes and sits next to you, maybe on a plane, and they take up all the space and you have no armrest. Okay, so they like to take up all the space. And then the bonds, they take up space too, but not as much as a lone pair. So because a lone pair takes up the most space, the radical will take up more space than a bond, but less space than a lone pair. Okay, so we have that idea there. So we want to go ahead and start now. What I'm going to work on is basically these tables here. So on slide number 8, but I'm going to add extra stuff to it. Okay, 8, 9, and 10. We'll be talking about these, but I'm going to go ahead and add the features from all the other components of this chapter in here as well. Okay, so while we're doing that, I want to start with the first thing here. The first thing I want to focus on is carbon dioxide. Okay, so when we think of carbon dioxide, what you have known before is only none of this stuff, just right there. Okay, just the Lewis dot structure. Agree? We learned how to count the valence electrons, We drew it out. We knew there's double bond on both sides, and then you have lone pairs around it. So now when we want to look at geometry, the thing that you want to focus on is basically carbon is my central. And then you decide how many electron groups do I have around carbon there? Okay, so you start counting. I have one group, I have two groups. Remember, a double bond counts as one group. Okay, a single bond is one group, double bond is one group, triple bond is another group. So carbon dioxide has two groups. And if you have two friends, you're stuck in the middle, they don't like each other, but you want to go hang out. What's the furthest way you can spread them apart from each other? Basically, one on the right side, one on the left side, and then they can't move a little higher up or down or closer towards you in any other direction, exactly 180 degrees away from each other. That's the most space they can get from each other. Okay, so that's the idea here. You're spreading two groups, and in fact, I want to show you what the molecule actually looks like. So if it was carbon dioxide, I'll explain why the double bonds look like this, but you see how these are double bonds here, and I'll explain why they are. But when you notice, double bonds can't turn, they're stuck. They can't twist, okay? So this is, when we talk twisting, sometimes you have things that you can take this guy and you can turn around. So we're saying we can twist these. Oh wait, I have to move it back here. Okay, you can twist the bonds and this bond can twist. See that? You can twist it. But when you have a double bond, it's kind of stuck. It doesn't twist, okay? It won't move, I promise. When we go to class, if you guys come to class, I'll let you guys play with these little models here. So anyway, so we have this, that's double bond, and that's as far away as possible from each other. If you notice, this is 180, that's 180 from this guy. If this guy goes a little bit closer in direction, let me zoom out a little bit. Hard to see. If this guy, the red one, starts to move a little closer that way, then you're like, hey, you're breathing my air. And then this one, if they go over here, from here, and if they move a little bit closer to this side, and you're like, you're in my space. Okay, so this is the furthest they can get away from each other. So that's why we have a molecule that ends up being linear in 180 degrees. We say because there are two electron groups, both of them are bonded. Okay, the reason why we have to consider how many of them are bonded is because if they're not bonded groups, they actually behave a little bit different, where your electron geometry and molecular geometry will be different. But if the electron groups are all bonded, the electron geometry and molecular geometry are identical. Okay, so because they're all bonded, there are no lone groups here. I wrote that down. The bond angle we determined to be furthest away from each other is 180 degrees. The geometry here is called linear because the molecule is in a straight line. And both the geometries, electron geometry and molecular geometry. Okay, now there's something else called hybridization. So this whole theory about VSEPR is saying that we can build on the fact that we know there's these guys, 1, 2, 3, 4, 5, 6. There's 6 orbitals here that we're going to discuss in our scope of class. Where we have, if you have two groups, it's because you are hybridizing the first two orbitals. So the hybridization is called SP. They're saying you can take an S orbital and a P orbital, you hybridize it, it turns into a linear geometry. That's the idea there, okay? So remember, we have 1 S, 3 Ps, and then 5 Ds, but we only go up to the first 2 Ds. Okay, so that is hybridization there. Now, the next thing I want to talk about was we wanted to talk about polarity of bonds. So carbon and oxygen are on the second period right there. We said the top here, everybody, even they're next to each other, they're all going to be polar. Carbon and oxygen is definitely polar because they're not next to each other, but away. So this one is like 1.0 difference in electronegativity. Okay, so because they are polar, when you have a molecule that's polar, you will draw an arrow. The arrow points to the negative side of that bond, okay? So if you had a bond just like this here, carbon and oxygen is more electronegative. Therefore, the oxygen is pulling the electron density. If you were to draw a cloud, this cloud is bigger than that cloud. Okay, so it's pulling this direction. So this side is the negative side of that bond. And then if you took a look on the other side there, you have the identical bond but pulling in exactly opposite direction. All right, so you have 180 pulling in the opposite directions and exactly the same strength because they're the same type of electronegativity difference. So when you have two opposing forces like that, okay, that is going to cause you to kind of almost have a tug of war, but both sides are equally strong. What happens? Nobody wins, right? You just tie. It won't move one way or the other. So they're not uneven strength, they're the same strength, so they cancel each other out. So therefore we say in this molecule here, carbon and oxygen bonds are polar, but carbon dioxide molecule is overall non-polar because the bond polarities cancel each other out. Okay, so that is our first molecule right there. Now let's take a look at our second molecule that I want to focus on. The second molecule that I want to focus on is going to be BF3. So when we drew BF3, we said BF3 was one of our exceptions where you were okay having incomplete octet. So that's the picture that we would draw, and it has nothing to do with the geometry. We were lucky with carbon dioxide that what we drew actually turned out to be the geometry. That's just luck. In this case, your BF3, when you draw the Lewis dot structure like this, it actually is not what the molecule looks like. So let's go over it, okay? So first thing you do is once we draw the Lewis dot structure, we decide there's 24 electrons, this one matches. Boron is okay having 6 electrons because the formal charges combinations are good. So you have 1 group, 2 group, 3 group around the central boron. So 3 electron groups, all of them are bonded groups, none of them are lone pair groups. So because you have 3 things and you want to space them as far away as possible from each other, this is how you should do it. You should space them out all on the same, like basically you can lay them flat on the paper, but they have to be 120 degrees away from each other. Okay, so it's 120 degrees away from each other. And then, you can just do it whichever way, I mean, it doesn't matter. But that's 120 degrees, okay? So what do you call this, guys? So the bond angle is 120 degrees. We call this trigonal planar because both of them are, all of them are bonded groups, they're no lone groups. Electron geometry and molecular geometry is identical, okay? Electron geometry, in this case, trigonal planar, because it's on one plane, and it's a triangular shape, right? So trigonal planar is the name for the electron geometry and molecular geometry. Now, because we have 3 electron groups, we have to take S, P, and P to hybridize them together. We have sp2. So I want to show you, if you look on your textbooks and on the slides here, they do show you like how things can hybridize. Well, there's some here. This is for sp3 and then all that. So, but I want to show you the chart where we have all the hybridization. So in this case here, we were talking sp2. So this is how sp2, we say you take 1 s orbital and 2 p orbitals, you morph them together, they hybridize into this form, and then we join them together, and that's why it looks like trigonal planar. Okay, and then they say if you were to look at the energy levels, it would look like 2s and 2p, and then you hybridize them and they become hybridized orbital, and the other p that's still out there just stays up there like that. Okay, so that's the idea of hybridization. You're taking the first levels, the lowest level of energy orbital, so it is in this case is sp and p. Okay, no, so sp2 is the name for our 3 groups. Now let's take a look over here. Now B and F is a lot more electronegative than B, so it's a polar bond where the electron density is heavy towards the fluorine side. But then you have 3 equally distributed in opposite directions for BF and BF and BF, and they're all pulling in opposite directions with the same strength. It's kind of like a three-way tug of war, and everybody's pulling the same strength. So they cancel each other out, nobody wins. So the bonds are polar, but the molecule overall is non-polar because the polarity of every bond cancel each other out, okay? So I just wanted to do a recap there, just remember, in this case so far, we've seen that a lot of times bonds, when they're all identical and they're symmetrical in some way, like evenly distributed, they cancel each other out even though they're polar. Okay, now when you start throwing in lone pairs, it starts making things lopsided. So I want to show you an example where we start having lone pairs around the central atom. So the example that we want to go over is SO2. Now we drew SO2 before this in class, and we said it had a resonance. Okay, another thing about resonance is, okay, it says here, for molecules that exhibit resonance, it doesn't matter which resonance form you use, the electron geometry will be the same. You know why? Because the electron geometry is about the actual molecule shape, and we know that the actual molecule is a hybrid of all the resonance form. Okay, all the resonance structures. So the molecule is a hybrid of these two forms here. So I tried to draw it out. Now again, now you have how many groups? So let's just pick one of them and say one group, two group, three groups. Remember, single bond is one group, double bond is one group, lone pair is another group. So there's three groups around sulfur, my central atom. So notice we can only do geometry around one central atom. Now, when you have bigger molecules, you have multiple central atoms. I'll show you how we can determine it. And you will see this in your labs as well, okay? And we'll be doing geometry of different, more complicated molecules in labs for examples, because we get to build them up. So electron group is 3. 2 of them are bonded, one of them is lone. 2 of them are bonded, one of them is lone. The bond angle now, they say it's less than 120. You're like, well, how in the world did you say it was less than 120? So what it looks like is at first, it was like this, okay? Now, electron geometry is directly dependent on just how many electron groups. It doesn't distinguish between lone and bonded. That's the thing here. So electron geometry says, oh, 3 groups, trigonal planar, okay? So that's the base shape here. And then hybridization says, oh, 3 groups, sp2 hybridization, because all it cares about is how many electron groups are there, okay? So electron geometry looks at how many electron groups, 3. Hybridization looks at how many electron groups, 3. This one is sp2, this one is trigonal planar. Now, when we want to look at the actual shape of the molecule, not just the electron geometry, we want to look at the molecular geometry. This we have to take into account how many of these groups are bonded and how many of them are lone. So because it starts off as trigonal planar for electron geometry, we know that there was 3 groups. And out of those 3 groups, one of them is a lone pair. So I remember I told you guys earlier that lone pairs take up the most space. So I have to replace it with something a little bit bigger cloud of electron. So at first it was 120 if it was all equal bonds. Now what happens when you put a big fat cloud in the middle? It's gonna push these bonds down closer to each other. Okay, so it was like this 120. Now they're going to be closer to each other, so they're less than 120 now. Okay, so that's why the bond angle there is less than 120. So this is what it looks like. I tried to draw it out. So when I draw it out, I like to try to put everything on a plane of the paper and say, okay, so that's less than 120. And then those are my 2 equal bonds. Remember, they're between single and double bond length because they're a hybrid of these 2 forms here, okay? And if you had to look at the molecule, they say this is electron geometry. Electron geometry sees the electron lone pairs and the bonds. Molecular geometry cannot see the bonds, so this is invisible. So if it's invisible, let me just go ahead and take it out so you pretend it's not, well, you don't have to pretend it's like actually not there, okay? But remember, this one gets squished closer together, right? So what's the bent geometry here? It's not straight, it's bent, okay? I kind of gave you the punchline, but it's bent, and that's why the molecular geometry is called bent right there. A very original name, I know. So that over here is how we see the molecular geometry. So you can't see the top, you can see that it's bent, it's not straight. That's why the name is bent from molecular geometry. Now let's take a look at the bond polarity. S and O are polar bonds. Okay, S and O are polar bonds, with O being more electronegative because O is smaller. So it's going to pull towards down here as negative cloud over here. And this is another negative cloud over here. And both of them are pulling downwards. There's nobody pulling the opposite direction. So overall, these bonds don't cancel out. The polarity don't cancel out. And overall, the bottom side, wherever the oxygen is always going to be really negative. And the top side where there's no oxygen is always going to be more positive. Although it's not actually ionic, so we can represent them by the partial negative charge and partial positive charge by writing this sign. So there's a little partial negative sign here and partial positive on the top wherever the oxygen is in it. So basically, I mean, wherever you can move the molecule around, but this side is always the negative side, this side is the positive side. Negative side is where the oxygens are, okay? So that is how you look at the difference between molecular geometry, electron geometry, and you can tell in this case, bonds are polar, the molecule is also polar because they did not cancel out. What happened is because there's this lopsidedness now because this one wasn't a bond to pull the opposite direction, now it's like just on the bottom there, okay? So basically, a lot of times, whenever you see lone pairs get put in, it makes things lopsided. But sometimes we do have cases where we put just enough lone pairs, it actually helps it cancel out. So don't always assume the existence of lone pairs will cause you to have polarity. That's not always true. You have to look at the situation, okay? All right, let's move on to the next guy. The next one we want to talk about, we want to graduate from 2 and 3 groups, we want to go to 4 groups, okay? So we'll focus on CH4, the methane group. When we have methane, we drew out there was 8 electrons, so C and single bond H to everybody. So in this case, around carbon, you have 4 electron groups and all 4 of them are bonded, okay? Now, because they're all 4 bonded, this is how you best spread 4 groups around. So you can't really see, but let me try to put it on a single plane. Okay, if you put it on a single plane here like this, see how this is a ruler here, right? So that's flat. Now I'm going to put 2 of them on one plane. They're laying flat. And when you lay them flat, what you see here, oh, you can't see. Have to get creative. Okay. You see how this is flat and then one sticks out from a plane, one goes behind the plane. Okay, so in that case here, you can also see by using this model here, is literally just these 2 things here, and you hook them up. They're pulling in opposite direction. So they're kind of like opposite. So if one side is flat on my hand or paper, you see one sticks out and the other one sticks behind the plane. Okay, so the way I have to draw it out, representing on piece of paper, the bond that's sticking out, I color in as a thick wedge, and this one is a hash wedge. Okay, hash is kind of like a shadow behind the paper. This one is sticking out because it's coming closer to me, so I draw it thicker. Okay, and what is the bond angle here? Sounds like a radio station, it's 109.5. Okay, so this is how you spread 4 groups around. So if I put them flat on a piece of paper, you can see there's sort of like a pyramid on the bottom and the top bond sticks out. So I have to kind of, so pretend like this here, like if everybody was on here on the paper, you see how this is one plane and there's a little pyramid on the bottom and this one sticks out. So that's what this 4 groups looks like. We call this group tetrahedral. The geometry is tetrahedral for electron geometry. And because there are no lone pairs, the molecular geometry looks exactly identical to the electron geometry. Because there's no lone pairs to take out, there's nothing that's invisible, it looks exactly the same. Okay, so in this case here, molecular and electron geometry are both tetrahedral. My hybridization, because I have 4 electron groups, I need the first 4 orbitals, so it's sp3. So let's take a look at what sp3 geometry looks like. How in the world they say it hybridized, okay? This was the sp3, so spp and you form 4 different things like that, and they say morph them together, you got tetrahedral. Okay, and then when you say SPPP, you hybridize them, they're all the same energy now. So if you had CH4 that we were drawing, so you have this purple, the purple things here, those are the hybridized sp3 orbitals. And the bond angle here is 109.5. Each one of them is 109.5 away from each other. Okay, now notice it's stuck to an H, right? So the H is just a little s orbital is stuck to it, and that forms the bond right there. We'll talk about this kind of bond in a little bit, okay? So in this case here, I told you to memorize CH bonds are nonpolar. Because it's a nonpolar bond, the molecule is also nonpolar. Okay, so we got that one. Now let's move on to another electron group that has 4 of them, but in this case, we have 1 lone pair and 3 are bonded. So out of those 4, 3 of them are bonded, 1 of them is lone. Okay, so we were at first like this. So because it's 4 groups, the electron geometry is still tetrahedral. The hybridization is still sp3. That one never changes based on electron groups. Okay, now let's consider, so we know this was what it looks like for 4 groups. And then now we want to take away one of those bonds and replace it with a fat electron cloud. Okay, so that's what I'm going to do, just put an electron cloud in there. So I'll flip it over so you can see. Okay, so see how there's a little pyramid on the bottom there, and that's a cloud. Now this big cloud here, it takes up more space than a bond, so it's going to squish these guys closer together to each other. So they, from here, they're squished down. Okay, I have to be careful because I've actually broken these before in class, and they flew all over the place. So you push it down closer, okay? So the bond angle is now less than 109.5. I would say it's close to around 107, okay? So because this part is invisible, okay, I'm gonna take this part off so you can see what the molecular geometry, and it looks like a little triangular pyramid, right? Little triangular pyramid. So we call it trigonal pyramidal. Okay, so the names of these guys here actually tell you the shape. So it's easier to remember if you understand where the name came from. They did not just make this up. Like, it's actually based on what it looks like. Okay, so this is what it looks like here when I try to draw in 3D. So obviously I put this one and the cloud on the same plane. Let me put that back in. Like that, okay? So these are on the same plane, and then you see how one sticks out, one sticks to the back. So that's how I drew sticking out and sticking to the back. Now, when we want to look at polarity here, hydrogen is less electronegative than nitrogen, so everybody's pointing upwards. So the electron density is pointing towards the nitrogen. The nitrogen is the negative end, partial negative end of the molecule. The hydrogen side is going to be the partial positive. So there's a polarity in this molecule where the hydrogen side, this side is more positive. This side here is going to be more negative up here. Okay. So in this case, the bonds are polar. The molecule is also polar for ammonia. So you can kind of see, depending on what electron groups there are, and what the geometry is, and the types of bonds you have. If you have polar bonds, you have to see if they cancel out or not. If they don't cancel out like this guy here, then then it's polar. If they do cancel out, they're evenly all the same, then they actually will be nonpolar. So let's take a look at another that's 4 group. So the other one that's 4 group here is water, H2O. We have 8 electrons. So you drew this before, okay? That's the Lewis dot structure, but it does not tell you anything about the shape of water. I like to say water is like the hidden Mickey. Okay, I'll show you guys why. So 4 groups, 2 of them bonded, 2 of them alone. 1, 2, bonded, 1, 2, lone, okay? Now, they say once you have lone groups, there are 2 and 2 here. This was what's earlier, right? We had that. Now we go one more step. We say take away 1 more, and we stick another electron cloud in. So let me go ahead and push that in. You're like, oh, look, that's the hidden Mickey. Well, kind of, my ears are a little smaller. That's the hidden Mickey, okay? So anyway, so this is what water looks like. The lone pairs are up here, and now instead of just 1, there's 2 of them. And when there's 2 of them, they were going to push these guys even closer to each other. So it was less than 109.5 before, right? Like we say it was 107. This one's going to be closer to 104, 105. Okay, so they're going to push them closer together because now there's two lone pairs squishing everybody else closer together. Now, electron geometry is still tetrahedral because there's 4 electron groups. Hybridization is still sp3 because there's 4 electron groups. Now, let's consider why the molecular geometry is called this name. So these guys are invisible, agree? So if you take those guys and they're invisible, we'll pull them out so you can see like, oh, okay, what does it look like? Well, it's not straight, but it is bent. Therefore, the name is bent. Again, it literally is bent, but the bond angle here is closer to 104, 105 degrees. Okay, the other bend that we just had, that was closer to like 120 degrees. It's less than 120. This one is less than 109.5. Okay, so that one is the bent for water. Now, when you say, we always say water is polar. We knew water was polar. So let's explain why. Because when you take a look at O and H, oxygen is the more negative, electronegative atom. So the electron density is centered towards the oxygen, and the hydrogen side is going to be the positive side, partial positive. The oxygen side is going to be the partial negative. So whenever you have water molecules, you have these guys are on the positive side. This one is the negative side. Okay, there's lots of water molecules. So I have seen, because we are nerds, they will literally take these guys and I have one here. If you make a ton of these guys, they're all water molecules, right? I guess you could put the lone pairs in, but that works too. I've seen where you have a bunch of these molecules all over the floor and they put a wet floor sign. Okay, so if you see that and you laugh, you might be a chemistry nerd. Actually, the meme that I saw, it says, if you laugh at this picture, you might have no friends. But I have friends, okay? So that's not true. Anyway, so that's that for our water molecule here, okay? Water molecule has polar bonds and this overall polar molecules because the bonds do not cancel each other out. Let's take a look at, now we want to take a look at 5 groups, okay? Now we have 5 groups. What does 5 group look like? So when we drew the 5 group, we had an example of expanded octet was PCl5. We drew like a little starfish. This is not what the geometry looks like at all, okay? So I wanted to show you what 5 groups looks like. It looks like this. You have 5 friends that can't stand each other. It's kind of like you have a linear right here, top and bottom, and then you have 3 groups in 120. So it's kind of like a linear and a trigonal planar combined together. Okay, so that's 3 in the middle and then 2 180 away. So depending on how you want to look at it, that's that right there. Okay, and then we flip it over. You can see that's the 180 side, right? And then there's the 120 side. So the bond angles you see on this guy, from here to here, that's 90 degrees. And then from here to there, these are all 120. Okay, so it's 90 and 120 bond angles, and PCl5, everybody is bonded, there's no lone groups. Therefore, the electron geometry is the same as the molecular geometry. Electron groups is 5, so SPPPD, so sp3d is my hybridization name. Okay, so then you can hybridize it to look like this when you want to draw it. I like to draw where I'm going to put 3 of them on the same plane. So 3 of them flat on my plane. And you see after 3 of them flat on the plane, there's one that sticks out and one that sticks back. So that's what I'm doing right there. 3 of them on a plane, 1 sticks out, 1 sticks back. And then these guys are the 120. From here, top to the middle is always 90 degrees. Okay, from here to the middle is 90 degrees right there. So those are my bond angles. I drew it out. Now, the bonds are polar. P and Cl bonds are polar, but because one pulls up, one pulls down, they cancel each other out. And in these 3 here, they cancel each other out. So overall, it cancels out and a molecule becomes nonpolar. Okay, so that is that for 5 groups. And the name is called trigonal bipyramidal. So why is it trigonal bipyramidal? It looks like there's 2 pyramids, 2 triangular pyramids, one on the top and then one on the bottom. Okay, So can you imagine if you connected the dots right there? That's a pyramid on the bottom, and then there's another pyramid on the top right there. Okay, so it's trigonal bipyramidal, because there's two pyramids, triangular pyramids stuck together. Okay, let's take a look when you have 5 electron groups and 4 bonded groups and 1 lone group. So the example we have here will be SF4. When we draw it out, you have 34 electrons, a single bond to the fluorine here. So the fluorine, remember halogen, they only can take, because of formal charge combinations, they can only take one bond. They like to have single bonds and to be on the outside, because the more electronegative, you got to put the outside. So in this case here, you end up with single bonds and you're like, hold on a second, I'm still missing 2 electrons. So you got to draw 2 more. So this is an expanded octet example. Okay, so the expanded octet, you have sulfur with 2 extra oxygen, 2 extra lone pairs. So 5 are electron groups, 4 of them are bonded, 1 of them is lone. So because it's 5 groups, the electron geometry is called trigonal bipyramidal, like this kind of in shape. Okay, so right there. And then hybridization is still sp3d. Okay, now hybridization is sp3d. Now let's take a look at what the molecular geometry will look like. So here's the thing. If you have 120 degrees and you have 90 degrees, you must put the electron group at the 120 because electrons like space. So I put the fat cloud on one of the 120s. You have to do it on a 120 because they can't do the 90. 90 is not enough space, okay? So this is what it looks like now. You put a big cloud, and when you put a big cloud in, what happens to the bond angles? This one is gonna shrink less than 120. From here to there, it's gonna shrink and be less than 90. So from here to there, it's gonna bend, okay? Bend in that way, and then this one is gonna bend in towards, because this guy is pushing everyone closer. So the bond angle is less than 90, less than 120. Okay, now you're like, okay, this side, this says seesaw. I'm like, I have no idea where they got seesaw from. So when I first saw this, when I was learning Gen Chem, I was like, you know, these people just made up names. It's so hard to remember. And then once I was reading and checking through it, I realized that the names actually are the shape. So there is a seesaw here. And you're like, okay, come on, show me where the seesaw is. I will show you where the seesaw is, okay? So remember, molecular geometry can't see the lone pair, so I'm going to take that big cloud out. This is still the electron geometry. You can see that on the electron geometry, so it's trigonal bipyramidal still. Now I'm going to go ahead and take this guy out, okay? And then we are going to put this on a playground like this, okay? So this is the playground and there's grass. I guess just pretend the paper is grass right here, or my hands are the grass, okay? Right there, okay? So that's a playground, and then you put a kid on this side and a kid on that side, okay? So when you go, seesaw, you guys see that? Oh, it fell over. Anyway, that is why you get seesaw. So this is the bottom of the seesaw right there, okay? You plant this in the grass, and then you sit a kid here, one side here, and then you put the kid there. The other one goes there. So it is a seesaw. Look how cute. This is literally, I think, like my favorite now. Okay, so SF4 is seesaw molecular geometry, and you actually get to see a seesaw. So there's that. Now, because it's a cool seesaw, we want to take a look at the polarity of this bond. I'll say S and F are polar bonds, right? So it points towards the F because F is the more electronegative, so it points out. That one points the other way. So these two kind of cancel each other out, agree? But what about these two? There's nobody canceling out on the top. So these two are pointing down. So everybody on this side here is always going to be the negative side, and this on the top, since nobody's canceling out, is the positive side. So SF4 is polar because the bonds are on the bottom here. They're on the more negative polar side of the molecule. On the top side here is the partial positive. So partial positive up here, partial negative where the fluorines are. Okay, so SF4 has polar bonds and they don't cancel out. So the polar bonds result in a polar molecule. So that was seesaw right there. Let's continue now. We want to talk about more in group 5. Okay, so group 5 here, we can keep going here. Oh yeah, I made a note here. It says polar molecule has dipole moment. And when you have the dipole moment, you point it to one direction, that's the negative side. You point the arrow towards the negative side. The more polar the molecule, the more percent ionic character, because it's the more polar it is, the closer it is to an ionic character. That's all. Okay, that's what it means. So sometimes they will like use it interchangeably. They're like, okay, well, this molecule is polar. Like they give you like a difference in electronegativity, and they're like, which one is the most polar, the biggest difference, right? The biggest dipole moment, the most polar molecule will have the highest ionic character. So let's take a look at another molecule that we want to draw. This one has an interexpanded octet. So BrF3 is 7 from Br, 3 times 7 from fluorine. You have total of 28 electrons. So when you have 28 electrons, you draw these guys as single bonds, and you're like, oops, there's only 24. So let me add 4 more. Okay, so overall in total, you have 5 electron groups around the central. 1, 2, 3, 4, 5. 5, 3 of them are bonded, 2 of them are lone. Okay, so that is the case where basically, where were we? This was the seesaw, right? Okay, so this was seesaw. What we want to do now is put another lone group in there. So remember we said the lone group will go where the 120 is. So I'm going to pull it out of another 120 right there, okay? Because we need to put it in the one that has more space. So that's the 120 right there. So now I have 2, okay? So these 2 here are going to be pushing all these bonds all closer to the opposite side. So these bonds, instead of 90, they're going to be slightly less than 90 degrees now. That's where the bond angle is right there. Now, because it's 5 electron group, the geometry for electron geometry is still trigonal bipyramidal. It still looks the same because you can see these guys. And the hybridization is sp3d. Okay, now let's take a look at the molecular geometry. It's called T-shape because these guys are invisible, right? So let me pull it out and you're like, okay, what does it look like now? Oh, look, it looks like a T. And that's why the name is called T-shape. Okay, so original, right? I love it because it's so easy to remember now. T-shape literally looks just like a T. Okay, so let's take a look at the bonds here. So when we have the bonds, and this is how I drew it out, right? They happen to be slightly less than 90 degrees. So F is more electronegative, so it's gonna pull up here, and these 2 are gonna pull the opposite. So yeah, these 2, they cancel out on the sides, but the top, nobody's canceling out. So over here on the top here, you can say this is partial negative. I don't know why I drew a positive right there. So over here, partial negative, over here is partial positive because of the bonds not being canceled out. So BrF3 has polar bonds and it's a polar molecule and it has a dipole moment, a permanent dipole moment because it's gonna be permanently there, okay? So these molecules are always gonna be that shape. So that one is BrF3. Now let's go ahead and go crazy. We add another lone electron group to the group 5. Okay, so XEF2 is that example here. We have 22 total electrons. When we draw it out, you start seeing that it's F, and then you got to put 3 groups of lone pairs in there. So 3, 2, lone of them are 3, 2 are bonded, altogether 5. Because it's 5, it's still called trigonal bipyramidal for electron geometry. Hybridization is called sp3d. Let's take a look and see why it's linear. So we were talking about how earlier we could only put the, electrons at the 120, right? Because if we had a choice between 120 and 90, electrons like, okay, I'll take 120 because it has more space. So the other 120 left is up here. So it's going to take that one out and push that one in like that. So now you're like, woohoo, I got 3 clouds here, right? And they're all like exactly pushing these guys. So this one's pushing that, this one's pushing there. So in the end, the bond angle has to stay at 180 from this to there, because these guys are invisible here. So that's why they say the bond angle from this guy is 180, because these guys are invisible now, right? The bond angle is from one atom to this atom to this atom right here. So it's linear and it's 180. And in this case here, this molecule Xe and F2 is pulling towards the F, right? Pulling towards the F. but then they cancel each other out. So the molecule is nonpolar overall, okay? So let's take a look at now if you had 6 electron groups. SF6 is an example where you have 6 electron groups. So sulfur is group 6, fluorine is group 7, 6 times 7 plus 6, you get 48 total. So when you draw them out, everybody has single bonds, okay? So when you have single bonds and you have 6 groups, this is how you would split them apart. So earlier trigonal bipyramidal, you would put a triangular shape in the middle part, right? This time here, because you need another extra group, you split them into 90 degrees. Okay, so let me show you this is 5 groups right here. The black one is 5 groups. And then the gray one is 6 groups. Okay, so the only difference is, you see they look the same top and bottom. There's the 180, 190 degrees. And then, but in the middle here, one has 4 and one has 3. That's the difference right there. Okay, so this 6 group here is called octahedral. Okay, so octahedral here is that shape. So it's 6 and 6, all of them bonded. So it's called octahedral all around. Because there's 6 electron groups, you have hybridized S, P, 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 and DD. So sp3, D2, total, you have 6 of them. Okay, now SF bonds are polar, but they cancel each other out. This one cancels that. This one's cancel that one. This one's cancel the other one. Now, when you want to draw it, I like to draw where these guys are on the plane. So the top and bottom, and then 2 of them are sticking out, 2 of them are sticking behind the paper. So that's how I'm drawing it like that over here. And the bond angles are 90 degrees. Okay. Hopefully you can visualize this, which is kind of cool. We have like little molecular models. Okay. So that one's that. Overall is nonpolar because they cancel each other out, and we know hybridization. So let's take a look if we have 6 electron groups and some of them are bonded, some of them are lone electron groups. Okay, so in this case here, our example that we have here is going to be for BRF5. And BRF5 tells you that over here, you have 6 groups, 5 of them are bonded, 1 of them is lone. So when you draw it out, you have 42 electrons. So 5 of them takes 40 and you got 2 extra. So it's like this here, and you pull one of these groups out and have put a lone pair in. So there's that, okay? And they're like, okay, what does this look like now? So the electron geometry is still called octahedral. Hybridization is still sp3, D2. Let's take a look at what the bond angle is. It says at first it was 90 degrees from everybody because before this it was all 90, right? Because over here is 90, over here was 90. Now because of this guy there, everybody gets squished. So they're all a little bit less than 90. All get squished closer to that side, okay? So octahedral, and then they say the name is called square pyramidal. So when you pull out this guy as if it's invisible, you can actually sit on a piece of paper and you can see, if I flipped it, there's a little pyramid that you can form, and the base of it is a square. So it's called a square pyramidal because that is the shape, okay? So when you draw it out on the geometry here, I like to put that guy and a lone pair on one plane, and then stick out and stick back in. So like that. Okay, so that's what I'm drawing over there. So overall, is it polar or non-polar? So we can see these guys cancel each other out, Br and F. F is the more negative side. So electronegative, out pair, and then electronegative, and that one pulls the other side, they cancel. But the top one, nobody's canceling him out, right? So over here, this is the positive, the negative side, and the bottom here will be the positive side because that one, nobody's canceling it out, okay? Square pyramidal right there. Let's take a look at if you have one more electron group added to it. So XEF4 is your example right there. Now you have one more electron group. So when you want to do one more electron group, you already put one in there. The next electron group better be on the opposite side. Because if you put one here, that's too close, and then these ones are further away from each other, right? This is 180 away versus 90 away. So you're going to have to go ahead and put it up here. Right there, okay? Now, when you have that, your bond angle is going to be 90 because the top and bottom are pushing equally. Look how cute they are. Okay, so that's 90. electron group is electron geometry is octahedral. Hybridization is sp3d2. Now the name is called square planar because it is a square on one plane. Square planar. Okay, so planar means on one plane. There's pyramidal, there's planar, so planar is flat. Okay, so when you draw it out, if you wanted to draw like the way I have it drawn, this is what it looks like. We got this like this. Okay, and then two sticking out, two sticking back. Okay, so in this case here, the bonds are polar, but they cancel each other out. So overall, it's a non-polar molecule. So hopefully everyone understands this. Now this here can be found on all the slides, basically like all these slides here in our lecture notes, okay? And they also show you how they can draw the bonds. I drew it out and I showed you what they look like. So you can take a look at these here. And they talk about dipole moment and how they don't cancel out. Some of them cancel out. So these are what we've just gone over. But basically, I use these molecules on this slide 8, 9, and 10 here to talk about all the different topics that we were going to cover. Okay, so I showed you hybridization as well. So the next thing I want to talk about is, remember I told you how like the double bond can't rotate, and I got to explain to you what in the world those bonds are. So there's these bonds called sigma and pi bonds, okay? So I got to show you what they look like. So we've been talking orbitals. So there's something called sigma bond and something called pi bond. It's just basically how the bonds are being shaped, okay? A sigma bond is when the orbitals actually touch each other. Okay, so then when they touch each other, that's sigma bond. A pi bond, they don't touch, they just do a ESP connection. They just have to align, they be parallel. And then sigma bonds, because they're touching, is a lot stronger than a pi bond. Okay, so I want to show you how that relates to all our stuff that we've been talking about. So right here. So sigma bond, we'll zoom out a little bit. Right here. So here's all my Lego pieces. If you see, I've been playing Legos today in class. Look how cute. Okay, I can't wait to play Legos with you guys. Anyway, these are cool models. I bought them when I was going to school and I kept them. See how useful they are? They're like probably older than you guys are. I'm gonna put them back together. And if you get crazy, we could probably build like a really gigantic molecule based on all this. Okay, I need to stop playing. Okay, we have to focus. Okay, we got to focus. I won't focus. Okay, let's put this aside. Okay, so sigma bond is when things are touching. Okay, sometimes it's a hybrid bond touching, sometimes it's s orbitals touching, hybrid orbital, and this is a p orbital touching. Or d orbitals can touch too. I mean, it's just anything that touches, physically bumps into each other and touch, okay? That's how you make a sigma bond. Pi bond is when you just align the p orbitals in like dot, 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 is ESP connection. So why is this important? Because a single bond is made out of one sigma bond. They actually have to physically touch. So I wanted to show you a picture. Earlier we were looking at the CH3, remember? See here? And then we said CH3 was a single bond, single bond, single bond. So this single bond is touching between an s orbital and a hybrid orbital. S orbital, hybrid, S and hybrid, S and hybrid. So they're made by 4 sigma bonds there because they actually physically touch. Okay, so that's why I say single bond is made out of 1 sigma bond. When you have a double bond, it's 1 sigma and 1 pi bond. So when you have to draw it out, okay, my drawing is not very good, but I'll show you drawing in the slides. Touching and dot, dot, dot connection, okay? That's a double bond is 1 sigma, 1 pi combination. Triple bond is 1 sigma and 2 pi. So you just have to touch, dot, 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 like on the other side. So I want to show you some different pictures and see if we can find them. Oh, look at this one. This one's a more complicated molecule. Yeah. Look at this one here. See how That one's sigma, 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 and then there's a pi bond right there, right? Because the pi bond is sigma and pi. This here is a double bond. So if you were to draw it out, see how the CO here, the C and O, that's my double bond right there. That's the double bond over here. So that's how you would represent it, okay? And then, so the C double bond O and C and an H, so that's the C and then the H right there. And then there's C and an H3 right there. So CH3 is over here. That's CH3 right there. And then CH and then C double bond O. Okay, so that's how you would look at it. So while we're looking at this one here, let's go ahead and we talked about hybridization. If you knew the hybridization, you kind of know the bond angles as well. Agree? So when this one here, this is what, how many electron groups here? So there's two central atoms here. So that's important when we start to talk about two central atoms. So this is the first one. This is the second one. We can talk about two different geometries here. The first central atom, C1 here, the geometry, electron geometry is tetrahedral because there's 4 groups. The molecular geometry is also tetrahedral because it's 4 groups. Therefore, I know the bond angles here are 109.5. So from here to here, from here to here, from here to here, here to here, they're all 109.5 degrees. Okay, and then say from here to here to here to here, this is my second center. My second center here, in this case here, I have 3 groups. So this 3 groups here, because there's no lone pairs around my carbon, is trigonal planar for molecular geometry and electron geometry. The bond angles are going to be 120. So this is 120. This one here is 109.5. Okay, so that's 120 right there. And you can see when they drew it out, see that's kind of like the 120, the sp2 hybridization right there. This is sp3 right here. The other purple is sp3. So I just wanted to show you now, when you have a double bond, you can't flip, you can't rotate it. So it's kind of like this idea here. This is the double bond. You won't be able to rotate. Single bonds can freely rotate, but double bonds cannot. Okay, so that's why double bond and triple bond can't rotate because they got the extra pi bond stuck on it. Single bonds, when they're touching, they can rotate whatever they want. It's so easy. Okay, so here's another example we can take a look at. See, this is BRF3 when they were drawing out. So this one, remember, there's 5 groups, and then there's the 2 lones. So it's 2 lone here. This is what it looks like, 5 groups. This is my 5 groups, and then I want to put 2 on the 120. Right there, okay? So this is what it looks like right there. And then they show you, oh, this is what the picture looks like. So it's single bond, single bond, single bond. So they're sigma, 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 they're touching, right? And then you have the lone pairs over here. And remember the shape here was T shape, okay? And then the hybridization obviously is 5 groups of sp3d. So that was that. Let's go another example right here. So this other example here is C2H4, okay? So C2H4, when you draw it out, you see a double bond in the middle, and there's 2 carbon central atoms, but they're both identical. So we can look at one and know the answer for the other guy is the same. So there's 3 groups, 1, 2, 3, okay? So hybridization is sp2 here, and there's gonna be a double bond in the middle. So you see how this is a sigma and a pi? That's my double bond between the 2 carbons. And these are my sigma bonds right there. And the bond angle between the C and H here. So this one here is, because it's 3 groups, it's gonna be 120 degrees apart. Okay, so that's kind of showing you where the bondings are. So I do end up drawing it. So in lab, let me show you guys what you see in lab. Just a couple examples anyway. So remember, single bond is 1 sigma, double bond is sigma pi, triple bond is sigma pi pi, okay? This is what you see. So when we drew these guys out, C2H4 solid, we just did that example on the slides there. So So this is if you had 14 and you draw it out, you're like, that's not going to work because my electron counts don't match. So you put a double bond in there, and this is how you would typically draw it out in Lewis dot structure because we don't know the geometry. But once you figure out it's 3 electron groups, you see that it's actually going to be 120 degrees apart. So when I draw it out, I like to draw 120. And the molecule here is nonpolar because CC is nonpolar, CH is nonpolar. It's trigonal planar on both sides. Okay. How many pi bonds and how many sigma bonds? So then you start counting single, 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 single. So that's 4 sigma, and this one is sigma and pi. So that's where there's 5 sigma bonds and 1 pi bond right there. Okay. We don't have to do P4 on your lab if you still have P4 on there. Right, and then CH4O is really CH3OH. Okay, and this is methanol. So you have 14 electrons here, and I want to show you what the methanol looks like. So it's CH3OH, and that's why this one is easier to understand than that. Okay, so when you draw it out, CHHH, and then you got your, this is kind of like what the water looks like. This is the hidden Mickey, remember? And except that was an H, now it's stuck to a carbon. So carbon has 4 groups here. So this is tetrahedral. This one is also tetrahedral electron geometry. The molecular geometry is tetrahedral here, but the molecular geometry here is bent because it's like the water that was bent. So it says here, carbon 4 electron groups all are bonded. So therefore, the first carbon, electron geometry, molecular geometry, tetrahedral, the bond angle is 109.5, hybridization is sp3. And then the second oxygen center here is 4 electron groups, 2 are bonded, 2 alone. So it's tetrahedral, but the molecular geometry is bent. It's the hidden Mickey that we talked about. Bond angle is closer to 104, 105, less than 109.5. Hybridization is still sp3. So when they draw it out, they don't show you the actual geometry because this is 109.5 and this is around 105 degrees. But they're showing you straight lines. So you want to make sure Lewis dot structure does not tell you geometry. So you have to like consciously put effort in to try to figure out what the geometry looks like. Okay, so while we're at it, we finished talking about all the geometries we wanted for the VSEPR, the valence band theory. So that was what we were just talking about, the VSEPR and the Lewis stuff. There are some problems. I guess it's not a complete theory. So some people are like, let's use another theory to try to replace it. So this theory is favored by the organic chemist. This theory here is favored by the physical chemist because they're all about quantum mechanics. So when they talk about quantum mechanics, molecular orbital theory, they're like, we can do it better. And the organic chemists will be like, well, we can do it better. Look at our model. So it's just another option theory. We're not going to focus too much on this, but I do want to show you a little bit about it, okay? So we want to form molecular orbitals. We want to form from atomic orbitals. So when you look at orbitals, remember we say there's wave and particle duality in nature, right? So we want to talk about how we can have 2 options. One, when you put them together like a wave, you can have destructive interference, and the other one has constructive interference. When you combine atomic orbitals, so they call it linear combination of atomic orbitals. That means you take the atoms, you combine them, you have 2 options. If it's destructive interference, you get anti-bonding molecular orbital. Anti-bondings have a star next to it. Bonding molecular orbitals are stable, are lower in energy, have no star next to it. Okay, so when you have, like say in this case, atomic orbitals, and you want to combine them together, you can have bonding, you can have anti-bonding. Anti-bonding is high energy, bonding is stable, is low energy. Bonding is from constructive interference. Anti-bonding is from destructive interference. So I want to go ahead and show you what it will look like, okay? So they have this picture here. It's much prettier than what I can draw. But so basically, hydrogen atom is 1s1, another hydrogen atom is 1s1. So when you have 2 atoms here, 2 atomic orbitals, will combine to make 2 molecular orbitals, where one is a bonding, lower energy, one is anti-bonding, higher energy. That's always the case. So the number of atomic orbitals you combine will result in the number of molecular orbitals you get. Okay, bonding is lower energy, anti-bonding is higher energy. So this one's really simple because it's 1s. You got sigma 1s, sigma star 1s. That's antibonding. Now, when we fill up the electron, this is 1 and 1. So we will fill spin up, spin down like that and combine them together. Okay, so there's something called bond order that we can calculate based on it. So bond order will tell you the formula is bonding electrons minus antibonding electrons divided by 2. So after you draw them in a molecular orbital diagram, you fill them in from the bottom to the top, and you count the ones in bonding, and you minus the ones in antibonding. We can get bond order that way. And you don't really have to consider, you could draw all the inside stuff, but the inside stuff kind of cancel each other out anyway. So you can focus on the valence electrons, and might be a fraction. The higher the bond order, the better it is. The stronger and the shorter bonds. Remember, strong bonds are shorter and thicker, okay? Higher energy. Bond order is 0, bond is unstable. So basically, once you have all this out, you can calculate the bond order. So I want to show you some examples, okay? So earlier we had the 1s and 1s, we put them together. So this is my notes right here. You obviously will get pictures of these notes as well. So let me zoom out a little bit. So the bond order is 2 in the bonding minus 0. So 2 minus 0 over 2, my bond order is 1 for this one. What if I went crazy and I want to combine a H atom and H plus ion? This one has no electrons, this one has 1. I'm going to put 1 down here. So it's 1 minus 0 over 2, because the formula is bonding electrons minus antibonding electrons divided by 2. So I only have 1 to fill in the bottom. That's why my bond order is half. So the higher the bond order, the better. So this one is a better bond than the second option that we just drew. Okay, so what if we went crazy and we were like, okay, let's do helium. I'm like, I've never seen helium, dihelium before. Well, let's do it, let's try it. So when you put dihelium, you got 1s2 and 1s2, 2 electrons on both. 2 atomic orbitals will result in 2 molecular orbitals. Bonding on the bottom, antibonding on the top, because it's high energy, unstable. And then you go 2 minus 2 over 0. Now this here is an unstable bond. Remember we said 0 is not good. So this one here, bond order is no good, not stable. And then we show you here, if you wanted to calculate, technically we can do just the valence. You could have done 2 minus 0 over 2. You would have still gotten 1. But if you drew everybody in there, you can calculate bonding is 4 minus 2 is antibonding, and you can still get 1. So you can do the same thing. I'm just showing you that if you counted the bonds on the inside, when you do the bond order, you should still be able to get the same number. But when you count the total number of orbitals, don't forget to count the bottom ones as well. So I'm not going to like focus too much about these kind of stuff, but that's bond order calculations. So you have to get familiar with bond order calculations on a molecular orbital, but I do not expect you to know what the orbital shapes will look like, because they do tend to get complicated. So this is dihelium, that's dilithium. We did that. And then I wanted to show you, so they draw pictures to show you how you can get bonding and anti-bonding, right? Now, when you start to have more complicated examples, this is when you see how when you go to boron, whoa, we can't see, focus, there we go. Okay, zoom in. So this is on slide number 53 here. When you have boron, carbon, and nitrogen, so this is boron side and that's boron, and then or carbon, carbon, nitrogen, nitrogen. The arrangements when they hybridize become a little bit different. When it goes to oxygen, fluorine, and neon, they're more electronegative here, right? So the bonding changes. So you look in the bottom here, they stay the same. So it's sigma 2s and sigma 2s star, sigma 2s, sigma 2s star. That's the same. They don't draw the level 1 because level 1 is, remember, it's literally like this, but 1s label, but it's on the bottom of these guys. It will be like below here. Okay, so this is just the outside, the valence part. So you have to remember there's also something else on the bottom besides what they drew on the outside. And imagine when there's d orbitals, that gets even more complicated. We're only at level 2 right here. So that's what I'm saying, like, we don't really need to focus too much about it, but I do want you to be aware that it is there. And if you have to fill it in, remember, fill the bottom first, and then you go up to the top. Now, the difference between boron, carbon, nitrogen, and oxygen, fluorine, neon here is when you have these diatomic molecules here, boron, carbon, nitrogen, it's pi and sigma, and then pi and sigma. So pi sigma 2p, pi star sigma star. Over here, you have sigma pi, pi sigma. So the arrangement is a little bit different. You see how this one is pi sigma, pi sigma? This one is sigma pi, pi sigma. This is a little bit different. So, but you still can fill in the bottom ones first before you fill in the top. Always remember fill the bottom and top. Now, because of this difference here, when you do bonding, when you calculate bond order, you have to remember which one's the anti-bonding and how do they get filled first. So the bond order might come out a little bit different. But that has to do with the types of bonding that they have. Once they mix the atomic orbitals, they behave a little different. So that's the only difference here between BCN and OF and E. Okay, this one is pi 2p, sigma 2p, pi star 2p, sigma star 2p. This one here is sigma 2p, pi 2p, and then pi star 2p, and then sigma star 2p. And then they go over all different kinds of examples. You can look at them. It's kind of interesting and cool, but you don't need to like worry too much about it. So that is the end of our chapter for us for chapter 11. And I will see you guys for chapter 12 and 13.